All right, so kind of the last big topic we're going to go through and cover are what are known as buffer solutions. Now, buffers are aqueous solutions that prevent substantial changes in pH. And that's very, very important because, like we've mentioned before, the human blood has a very narrow range of pH. It has to be heavily buffered to prevent changes in pH because that keeps oxygen transport optimal if we have a pH range somewhere between 7.3 and 7.5. So in order to be a buffer, we have to have two things. We must have a weak acid or base and its conjugate. Now, often the conjugate base is given as a soluble salt of the conjugate base. So, for example, HCN, we know is not one of our 7 strong acids. But sometimes what we'll give is a salt that's associated with it. So if I were to add in the conjugate base, I don't just have Cn minus ions just hanging around, so I add some potassium cyanide, and that gives me my Cn minus ions. So it has to include something that's weak and its conjugate in order for it to be considered a buffer solution. Remember that conjugate acids and bases only differ by a single hydrogen as you go through and take a look at some of these practice problems. So what I'd like you to do is take a few minutes and determine if the following would work as a buffer solution. Remember, we need to have an acid and its conjugate base. And furthermore, it needs to be a weak acid as well. So keep that in mind as you go through and evaluate these, and then we will move on here in just a moment. Well, I didn't mean to jump ahead and go through and do all of this before you got a chance to kind of do it along with me. However, I realized I went through and did all of this, and yeah, I was not recording. So I have done all of the work and mentioned all of the things without recording. So let's look at this individually and break this down. So for A, remember, when we go through and do this, we need to make sure that we have a weak acid or base and its conjugate. And if we look at HCl and NaCl, remember that we can disguise our conjugates as ionic compounds. Remember that NaCl will dissociate, so we'll get Cl minus out of that. So what we end up with in solution is HCl and Cl minus. Albeit this is an acid-base conjugate pair, HCl is strong, so this is not a buffer solution. HCN and KCN. KCN produces cyanide minus ions. So that gives us HCN and CN minus. They are a conjugate acid-base pair because they differ by a hydrogen, and HCN is weak, so that is a conjugate acid-base pair. And then the third one there, is acetic acid, HC2H3O2, and sodium acetate, NaC2H3O2. That will dissociate and produce C2H3O2 minus ions. So we end up with HC2H3O2 and C2H3O2. That is a conjugate acid-base pair, and it's a weak acid, so that would be considered a buffer solution. And then lastly, we have NaCN and KCN, and there's no acid there. And when we don't have an acid, we don't have a buffer. So again, pretty easy to determine if we have a buffer solution. We just need to look at our chemicals that we have available. First off, we have to ask ourselves, do we have a strong or weak? We have to ask ourselves, do we have a weak acid or base? Do we have its conjugate? And if so, then we can be considered a buffer solution. So that being said, I will try to remember to hit record for this before I start yapping away. Let's move on. So this slide here really drives home the importance of buffer solutions inside of the body. As we mentioned before, the pH range of blood is very, very narrow, in this case between 7.45 and 7.35. If we just differ ever so slightly from that, we end up with what's called alkalosis, which is a blood solution that's too basic, and acidosis, which is a solution that is too acidic. And you even deviate a little bit further from that, and the individual can no longer survive. The oxygen-rich environment of the blood no longer functions the way it's supposed to, and as a result, person's dead. So buffer solution is very, very important. And what they use in the blood is what's called carbonic acid. It's H2CO3 and HCO3 minus, and that acts as your buffer solution. But how do buffer solutions work to mitigate changes in pH? Well, let's take a look and see how they work. So let's consider the HCN-KCN buffer solution that we've taken a look at previously. If we add an acid, it will react with the base in the buffer. So if we think about what makes an acid, it's the H3O+. So you notice how I am reacting this. So H3O+ gets put into the solution, and it reacts with the conjugate base, which is the Cn-. Acid will donate its hydrogen to the base, and so what you end up with is HCN and H2O. So my products no longer have the H3O+ in it. Remember, it's the H3O+ that makes the solution acidic and the OH- that makes the solution basic. So as a result, we've mitigated the acid that's in the solution. And what we've actually created is the conjugate acid that's already in our buffer solution. We're creating HCN, which is a part of the buffer solution in and of itself. Adding in a base will react with the acid in the buffer solution. So if we add in something that produces OH minus ions, it's going to react with the HCN, and the HCN is going to act as an acid and donate its hydrogen to the OH minus, resulting in H2O and CN minus. So you notice that regardless of whether we add something that is acidic or basic, the opposite of it will react and it will produce water and then the other component that is part of the buffer solution. So when an acid reacts in the buffer solution, we get HCN and H2O, water. When a base reacts, we get CN minus and H2O, which is water. Pretty neat, isn't it? So again, as we figure this out and we figure out what we need to write, we need to consider, okay, are we putting in an acid or are we putting in a base? If we're putting in an acid, H3O plus is going to be one of our reactants. It's going to react with the base. If we're adding in a base, then OH minus is going to react, and we're going to react that with the HCN. Both will produce water and the opposite component that is a part of the buffer solution. Let's see how that works here in just a moment. So here what I'd like you to do is I'd like you to write an equation for each of the following buffering actions in these solutions. So what happens when we add H3O plus to an HFF minus buffer solution, and then when we add OH minus to a carbonic acid solution and a phosphoric acid solution? Take a few moments, think about it, and we'll be bringing you back in just a moment. All right, so as we go through and finish this up today, again, we have our buffer solutions here. We know these are buffer solutions because these are weak acids and bases and their conjugates, which is fine. But as we write these out and figure out how to write out buffer neutralization reactions, we need to first take a look here. We're adding an H3O plus, so we're adding an acid. So remember that the acid is going to react with the base that's in the solution. So when I start writing this out, I write H3O plus. They're all aqueous except for water. It's going to react with the F minus, which is also aqueous. When this happens, we end up with a transfer of hydrogen from the H3O plus to the F minus. And so what we end up with, as we talked about before, is water, because the H3O plus is going to lose a hydrogen. And then the hydrogen is going to get transferred to the F to make HF. So again, notice I neutralize the H3O plus by producing H2O and F minus. Quite convenient. This one is a base, so it's going to be reacting with the acid in the solution. So we start off with OH minus. It is aqueous. It reacts with the H2CO3, which is also aqueous. And what we get out of this, I should mention we should put double arrows here. These are buffer solutions. Buffer solutions are always in equilibrium, so we use the double arrow here. In this case, the hydrogen is going to transfer from the acid to the base, just like what we described previously. And so what I end up with is H2O, liquid, and H2CO3. Oops, sorry. HCO3 minus, which is aqueous. Okay. For us, we don't need to worry about going back and like balance equations, anything like that. These are already going to be balanced because all we're doing is transferring over hydrogen. So pretty easy to do that. Same thing here. We have a base. It's going to be reacting with the acid. Remember, we only transfer one hydrogen over. Don't transfer them all over. So we start off again with OH minus, which is aqueous. We're going to react that with H3O or H3PO4. Again, that hydrogen ion is going to transfer. So from the H3PO4 to the OH here. And we end up with some H2O, again liquid, and H2PO4 minus. Okay. So again, it's pretty easy to do. You just need to recognize if you're starting with an acid or starting with a base, and then figure out that it's going to react with the opposite component in the buffer solution. You're always going to produce water and the opposite component of what's in the reaction of the buffer solution. So in the first one, we used F minus as a reactant. We get HF as a product, both components of the buffer solution. And you see that across the board, all right? A few more things, and I think we will wrap things up in just a little bit. So what I want you to notice is how this mitigates changes in pH. Remember that the amount of H3O plus and OH minus determines how acidic or basic a solution is. So buffer solutions do a really, really good job of preventing that from existing in the solution. Remember that when we add H3O plus, it's going to react with the base in the buffer solution and prevent the H3O plus from changing the pH. And the opposite's true if we're adding in a base. It's going to react with the acid in the buffer solution to prevent OH minus from reacting. But notice that in pure water, if I just add small amounts of OH minus or H3O plus, notice how much the pH changes. Just a 0.01 moles of OH minus can raise the pH of something with a pH that's close to 7 all the way up to a pH of above 12. And we add H3O plus, we can lower it all the way down to 2. But in a buffer solution, notice how very little that changes the solution. So buffer solutions do a great job. Now, this isn't going to work infinitely. Okay, a buffer solution is only as good as how much of the buffer solution you have or how concentrated the buffer solution is. You can eventually run out of acid or base to react with, and then you do see large changes in pH. So the amount that the buffer has the ability to mitigate is dependent upon its concentration. A story for another day. Another way that we can look at relative strengths of acids is by looking at what's called the pKa. We won't spend a lot of time talking about pKa. It's the negative log of a Ka value. K is an equilibrium constant for an acid. You don't have to worry about it much. Just the lower the pKa, the stronger the acid. Very similar to how you think of pH. The lower the pH, the stronger the acid. The lower the pKa, the stronger the acid as well. And so lastly for this unit, and there'll be other things that I add, I'm actually going to go through and rearrange this a little bit later on, but we can calculate the pH of a buffer solution by using the Henderson-Hasselbalch equation. This is where the pH of the buffer solution equals the pKa of the acid. I'll give that to you. And then you just simply need to plug in the concentration of the base and the acid and take the log of that, and that will indicate whether or not the pH is slightly above or below the pKa. You need to think about this as well, is that if I have a pKa value, which is representative of how strong an acid or base is. If there's a little more base than acid, that should cause the pH to be a little bit higher than the pKa value because you have more base, right? More base in the solution means that the pH should be higher. And if we add in more acid, then the pH will be a little bit lower than the pKa. So you can use this as a way to really think about, did I go through and do this math correctly? So we got one more practice problem, and then we will be finished. So being finished, here's the last practice problem. I give you some concentrations of some acids and some bases. It asks you to calculate the pH of the buffer solution. Do that, and we will be done and finished. We'll see you here in just a moment. All right, so the very last problem here, it does ask us to calculate the pH of a buffer solution with 0.01 molar HNO2 and 1.0 molar NO2 minus. So this is the acid in my buffer solution. This is the base in my buffer solution. We're given the pKa, so this just simply becomes an algebra problem. So pH equals your pKa, which is 3.15. Plus the log of the base over concentration of the acid. Now, the base is in higher concentration than that of the acid, so the pH should be a little bit above 3.15, should be a little bit higher than the pKa that's listed here. So let's find out if that's true. So pH is going to equal 3.15. I'm going to simplify this just a little bit. So we'll take 1 divided by 0.01, and we'll take the log of that value, and what we get is 2. All right, so pH is 3.15 plus 2, so that is 5.15. Okay, so does that correlate with what we said up here? It sure does. The pH is slightly higher than that. Yeah, quite a bit higher because this is a very vast difference in concentrations of acid and conjugate base, but you get the idea here, okay? So this is just, like I said, a quick 1-hour overview of the material that we have in chapter number 10. We'll flesh this out more in class, but hopefully you enjoyed that. If you did, like, subscribe, etc. We will see you very soon, and have a fantastic day. Bye, everybody.